Great. Well, thank you so much, Rowan, for inviting me today. So I have some work, as you mentioned, where I use AI as sort of a tool, really, not sort of as the ultimate objective. But I thought I'd start with a maybe slightly broader perspective on where I personally see what sort of benefit AI may have for economic research. And so I try with a slightly broader perspective in the beginning. So where I speak, let me see, where I speak about some recent applications of machine learning in economic research. I then sort of shed light on like one particular aspect where I personally see machine learning to be of great value, and that is for data curation. And then I provide like two examples of my own work, one on state government debt structure, which is really like a data collection effort. And then the second application in an asset pricing paper of mine, where I use machine learning as for feature selection as well as function approximation. But let me start with some recent applications of machine learning. So this is by no means like a comprehensive literature review, but I just want to give you sort of a few examples and broadly categorize them, how economists have been using machine learning or AI. I guess for the sake of what we're doing today, it's really about machine learning in economic research. So the first sort of broad category is really thinking about sort of clustering. That means clustering is usually like some sort of dimensionality reduction and similarity analysis of getting a sense what is close to each other. So the first paper is, and I have all the references in sort of the backup, so please feel free to take a look at the original paper. But one sort of big advantage of machine learning is that suddenly we cannot just deal with like numerical data, but also with textual data. And so that has like broad applications in a variety of contexts. So for instance, to categorize and assess patterns. So patterns, is obviously a sort of an very important topic for economists because it sort of regulates the process in which innovation can take place. The second paper here is by Gabe, Koy, and Yogo. They use really like the sort of the recent idea of embeddings for like assets. That means like stocks and bonds in the financial market, to think about, well, how can we describe investor preferences over these assets in a sort of low dimensional space. And for that, they essentially define the investor preferences over the embedding space rather than over the space that is spanned by the raw data. Then another sort of interesting application, and sort of that has that's a model that has been widely used in economics, even though there are certainly shortcomings, is an LDA model, like a latent Dirichlet allocation model that essentially classifies a certain text corpus into topics and a topic distribution. And so that has been used, for instance, to assess the impact of state-level legislation on economic growth, or the second paper by Lars and Torsund to classify news stories in Norway to assess the extent to which it sort of precedes certain economic conditions. And so lastly here, with regard to clustering and similarity analysis, is the paper by Ash, Chen, and Ailu that uses, once again, word embeddings to sort of think about how does the opinion of judges have changed after attending like the Manne Institute. Okay, the second broad category that I've seen in recent research is using, particularly natural language processing for classification. So, obviously with COVID-19, we saw a big increase in work from home. And so there's the sort of the question, to what extent do like employees want to work from home, and to what extent do employers offer work from home? And for that, economists have used various models in order to classify essentially whether a job posting offers remote work or whether it doesn't. So that's, for instance, here in this first paper by one of my colleagues, Nick Bloom, he at Stanford. Then the second paper uses a slightly different method, but essentially also looks a little bit on sort of the skill content within jobs. So they try to classify to what extent a job is repetitive, monotonous, or whether it's more like a non-routine or an analytical job. Lastly, we have, once again, a slightly different method, but a similar question about, work from home in the UK. Sorry, I was jumping the wrong direction, but here we go. So the second last category that I want to briefly highlight is for sentiment analysis. So that's, has been particularly sort of popular in the context of monetary policy. So the first example, and there are a few other examples that fall sort of in the same category, they try to construct a sentiment index from the speeches that central bankers gave, during interviews, but also during like sort of formal press conferences. And so the question is to what extent that can forecast future economic conditions, particularly employment, inflation, as well as the financial market. There are a few authors that have done sort of a slightly more, I would say, custom way where they actually try to train a model, like the paper by Hang, Wang, and Yang, actually trains a Finword model, which they claim can identify the sentiment from text. So this is actually newspaper text better than a regular word model that is not specifically trained. So then the last thing that I want to highlight, and here I will go into much more detail later on when I speak about my own work, is really like functional approximation and feature selection. And so specifically, that has sort of yielded pretty significant advances in the asset pricing context. So feature selection generally arises from the problem that we have a lot of information about the macroeconomy. So in my case, I have more than 200 time series, but usually like the number of returns that we observe for an asset is rather limited. If you think about a stock, well, a stock belongs to a company. There obviously is companies like Coca-Cola that have been around for a long time. But if you think a company like Tesla, I'm not exactly sure when they IPO'd, but I think it was in 2014 or 15. So that means like we have only like an 8-year-long time series, which actually gives us relatively little return observations to work with. And so there generally that is known to be like the K larger than N problem, for K stands for the number of features and N the number of observations. And so we have to come up with a method in order to select a parsimonious set of features that allows us to work with in an asset pricing model. The other big application in asset pricing is function approximation. So asset pricing is almost synonymous of saying we want to find the stochastic discount factor. The stochastic discount factor is essentially a random variable that allows us to price all the assets in the economy as under a no arbitrage condition. In the past, we have been sort of constrained by the type of models that we could feasibly estimate. And so what the literature has always, preferred is sort of a linear assumption about the model, and just saying that this linear model is probably the best linear fit to a more generic class of models. But more recently, I think after 2019, 2020, we have seen several authors starting to experiment with sort of more flexible model architectures that can, both incorporate like nonlinearities, but also like interaction between features. And so I think this is a very promising avenue for asset pricing research. And I'm going to speak a little bit more about that later on. Okay, so now let me come to one topic that we haven't seen that much in the past literature, which I think is probably the area with the largest potential, even though it may not be the most the most sexy topic, because ultimately it's data collection and data cleaning. But let me just give you a slightly broader perspective. So over the last 20 years, economics has more and more evolved into an empirical discipline. And empirical research is always constrained by the amount of data that is available. And typically economists have sort of given great preference to administrative data. So that would be like something like unemployment records or test scores in the school context. More recently, economists have more and more adapted sort of commercially available data sets. That is also just a sort of a reflection of the proliferation of data in the economy overall. But once again, and either administrative or commercially data sets are always, by definition limited and does not necessarily cover really the area that we're interested in terms of research topics. So there are certain types of data that have traditionally been collected in the economic context, but that is usually survey data. So that would mean that the researcher would specify the survey questions and then distribute the survey and then basically work off these survey responses. Or another very prominent area is experimental data. So that is, maybe you have heard about randomized control trials, where essentially the researcher designs an experiment and then gives like different treatment to different subjects, and then you work off from the data that you collect in that way. However, I would say probably the most sort of prevalent data set is actually observational data. So this is just observational data, whether these are prices that you observe or whether these are, movements of people that is being tracked. But this data has typically been sort of manually collected. And so the problem is that whenever you can't collect data, it's very hard to scale because sort of the effort is proportional to the sample size. And also, like, if you once you employ more than one person to collect these data set, it's obviously prone to inconsistencies. But also, if you have like a single person collecting a lot of data, the attention is just decreasing over time, and that can lead to a variety of mistakes. So here, I think machine learning has really quite a broad potential for collection as well as the cleaning of the data. And so has really the potential to broaden the scope for economic research to those topics that have previously been inaccessible or have previously seen a lack of data. I want to go into a little bit more detail about the data collection, data curation, and I really want to break it down into sort of the low-level steps and shed a little bit of light where I see machine learning to have an impact. So the first thing is that it usually starts with a certain data segmentation or selection, because the researcher is often confronted with a large amount of raw data, and usually for the particular research question of interest, only a sort of a subset of the data is really relevant. And so we have to make a first selection. In my case, I've been working a lot with PDF documents. And so for me, it was actually important to take these PDF documents and actually segment it into different content components. This includes like tables, titles, headers, the raw text, the text in between, and potentially figures. Another interesting aspect of machine learning that I have seen is in the case of newspaper articles. Here we have, another challenge. For the reader, it's very sort of user-friendly if the text is broken down into multiple columns, because then each line isn't that long, and so that makes it convenient. But for a researcher, that sort of creates an additional challenge that we actually have to segment these text columns and have, after this segmentation, we can extract the text. There's a recent model that has only been published about 2 weeks ago, which seemed to have achieved incredible accuracy, which is called Surya, that really allows us to segment these text columns, and after this segmentation, we can extract it. So just want to flag that here because that's, I think, a very neat recent development, and depending on what type of data you're working with, that might be actually quite helpful. Lastly, even after the segmentation, we usually have to do one additional step, and that is sort of the final selection of the content that we're trying to extract. And so in my own work, what I found actually quite convenient, because I work mostly with text data, I use like medium-sized, fine-tuned language models with a classification layer to essentially do like a selection of the content that I need. And so I go into that in a little bit more detail. Then sort of the second step, once we have selected the relevant content, there's the question about how can we extract these data. And here, I just want to briefly mention sort of two methods. Obviously, OCR has been around for quite some time, and it's obviously sort of freely available and achieves very good performance. There's one additional method which I just want to flag here. I have experimented a little bit with it, and that is function callings via large language models. So this is potentially an interesting approach because we can essentially use an LLM and specify a fixed output format, and the LLM sort of passes all the tags and tries to deliver only the fields that we have been asking for and get that back into a very nicely structured format, which is then available for downstream tasks. So there are some, in my personal experimentation, there's like some issues with it, but I think over time, that method may have great potential as well. So the next step in the data curation process is, typically known as data cleaning. Every research assistant that has worked with me went through reams of data collection. And, the current paradigm has been to use sort of an iterative, deterministic manipulation of the extracted data. For instance, it takes care of, harmonizing the unit of account, rearranging the data into a consistent data format, correcting typos, and do all sorts of other transformative operations. That works okay, but this deterministic manipulation is once again doesn't necessarily scale. And so that is particularly true if the input format has a lot of heterogeneous data formats, because because of the deterministic manipulation, we have to specify essentially for each data format one specific manipulation method. And so that sort of is a little bit of a limitation, which means that once you scale up the project, the effort remains once again somewhat proportional to the amount of input data. Just to elaborate a little bit on these points, so in deterministic data cleaning, we usually, specify, replace or transform operation in a specific and fully specified manner. So give you the example here. There's this word HEUS or HEUS, which maybe is a typo and should really be in house. Or we can apply a function of f on x equals 2x, which is uniformly applied to a numerical variable. In principle, you can do these for all the different data formats and then come up with a clean data set. But once again, this is somewhat, it doesn't really scale very well if you have a large amount of input formats. Instead, what I've been experimenting with and actually have applied quite successfully over the last year is what I call stochastic data homogenization. So here, how does that work? Rather than sort of specifying a deterministic data transformation, I specify essentially a sort of provide like in context examples to an LLM and then feed in my raw formats, and then the LLM will do the transformation that is consistent with the examples that I provided. So very specifically, I can give you an example. I used GPT-4 in my context. I provided about 10 or 15 examples about how this transformation is supposed to be, and then I provided or I applied it to all the different formats that I have seen in my data set. This has worked great, to be honest. Obviously, that does come at a pretty hefty price tag, because if you provide like large sort of examples to GPT-4 and then you provide all the raw data, I think we spent close to $10,000 just on data cleaning. So that's something to keep in mind. But certainly, with the proliferation of other large language models like Mistral, the cost will come down by orders of magnitude in the next couple of years. Oh, okay, sorry. So the practice is, while neither deterministic nor stochastic data transformation gets you all the way, you probably use sort of a combination of the two approaches. For example, in my paper, I use sort of the deterministic data transformation for all sort of numerical tasks, including unit normalizations, as well as sort of transformation of cash flows from one format into the other. You know that, LLMs are still, I would say, somewhat premature when it comes to numerical tasks. However, it is really good when we use LLMs for the transformation of column headers, transforming the sort of multi-column headers into a unique homogeneous format, as well as all sorts of typos or labeling of the same concept with different labels to homogenize those labels. Okay, so with the sort of these preamble, I just want to dive into one of the examples that draws on my own work and in the context of state government debt structure. So in the paper, essentially, I study what is the composition of state governments, so the 50 states in the United States, as well as what are the determinants of the debt structure of those governments. And so for that, I'm drawing onto annual financial reports of state governments, which are very similar to annual reports of corporation, in case you have worked with those. And these financial reports contain granular information about the debt structure, debt maturity structure by the issuer type, as well as the debt type. However, these financial reports, unlike for corporation, have only been published in form of PDF documents. And some of them are machine readable, some of them are not. Some of them are kind of ancient, that have been scanned from the paper version of those reports. And so these this variety of formats, as well as just the sheer amount of data, has it historically made very difficult to collect these data systematically. Just to give you sort of an impression about the size of the data, so we have obviously 50 state governments. We also included this District of Columbia, as well as Puerto Rico. We do this whole exercise for 16 years to sort of study the temporal variation. And then each of these financial reports is approximately 500 pages long. So in total, we deal with PDF documents that have more than 400,000 pages. And so, we obviously in the beginning, we thought about how can we extract these data, and it became quite obvious early on that like a manual data collection in these contexts is out of question. And so, in addition to just the form factor, that means like these, somewhat intractable PDF documents, there's a whole set of another issues that we had to deal with. And that includes, for instance, that the data is presented in very heterogeneous formats. That means like we can have like one state government is presenting the same information in one table format, the other one is presenting in another. And in addition, we have to deal with all types of unit harmonizations, because like the unit of account could be dollar billions, dollar millions, dollar thousands, or just dollars, or as well as sort of an homogenization of the terminology, because different state governments use slightly different expression for the same debt type. So how do you go about such an exercise, and how did I do it? So, in principle, there's a whole set of sort of pre-trained models that one could use off the shelf, but it turns out, maybe not surprisingly, that those models perform okay. But if you go to like a very specific context, as is mine, the accuracy is insufficient for like research purposes. And so instead, we had to build essentially a sort of a more customized approach, in which we started to label about 1,500 pages manually. And so these includes like positional information, including like the location of tables and titles and the text, as well as the unit of account of the specific table, and also the type of information that is being displayed in the table, that includes like the issuer type as well as the debt type. Obviously, just doing it sort of ad hoc and taking the first 3 reports to label 1,500 pages would be highly inefficient, because we have only like a small section of the annual report that is really relevant for us. The other one is sort of all negatives that we kind of want to sort out. And in addition, we want to, obviously there's a lot of variation in terms of formats across the different states and across the different years. So we wanted to train essentially, or we wanted to find those pages that are really important to improve the accuracy of the model for our specific context. And so we started to strategize this labeling process in the sense that we try to narrow it down to the reports where really the important information is. We try to sort of get like a cross-sectional sample of all the states, as well as sort of a time dimension to get a little bit about at the sort of changes in the format over the years. And then once we had a first sample, we try to so intersperse it with some negatives, just to get essentially also like a sample about when not to recognize a table, and as well as as well as, or that's actually on the next slide. Let me go to the next slide. So once we had a first sample, we essentially trained a first model. But then obviously, once you do the first inference, you find that a specific use case or specific formats will be predicted already with very high accuracy. Other ones have room for improvement. And so we basically started to play with these iterative procedure between labeling as well as model training to get as close as possible at those use cases that are really important in our context. And so for that, actually, we had to build a decent amount of tools in order to do these. So specifically in my context, I used Label Studio, which is an open source tool that runs on a local server. But then we essentially built like the interface to Python to really do like an efficient model iteration and labeling, where we could essentially import the previous labels. We could then correct them, on the screen on the user interface and redraw, for instance, the boundary boxes of specific, headers as well as tables. And then with these updated labels, we would retrain the model, we would repredict it, and ultimately we actually achieved an accuracy over 99% based on like a test on the test set. So it seems like we got to a really great benchmark, and we've been really happy that we now have a model that we can hopefully use when new data in the following years come in. Okay, let me just add maybe one additional point here. So we have essentially, or let me actually show that visually, that might make it much easier. So let me show you how our input documents look like. So we have essentially, this is a page of the annual comprehensive financial report. There's like sort of the title here. We have the title of the table. We have the table itself. We have some text in between, and then we have another table. And so for the boundary boxes, I used a multimodal vision model, which uses both the positional information as well as the text information to essentially predict the boundary boxes that you see on the right side. So what we try to do is essentially predict the table boundary box as well as the boundary of the table title, and so, which is here shown in red. So that's done via the vision model. And then we had to add one additional, or basically set two additional models to get two more pieces of information. First of all, we wanted to understand what is the unit of account of the specific table, because that has to be harmonized in the end. And then also we wanted to know what is the type of what is sort of the content type of the table. So this stands for maturity, general government, revenue bonds. Okay, so this is like one specific type of debt that governments issue, whereas this one is actually irrelevant, this table, and this debt is labeled as other, which we ultimately discard. Okay, so let me actually stop very briefly and just ask for some questions, because I go then into a different example.
Folks, are there any sort of, I think that I have like so many questions, but are there any sort of questions that folks want to raise at this point? If you just raise your hand. Thomas?
Well, I just wanted to know if you experimented with other PDF to text conversion tools, like there's Apache Camel, or you just went directly into the technique that you showed here.
Yeah, so we use a lot of packages to actually get the data. Once we have these boundary boxes, we then have to extract the data and get it into we use a Python, like a pandas data frame. And for that, we used like a package which we called Camelot, which is a really good package. It works well when the PDF is machine readable. It doesn't work when it's an image. For that, we actually used AWS text extract, which is, to my knowledge, the best model out there right now for tabular data. But regardless, you first of all need the boundary boxes. Otherwise, it doesn't really work because it would not properly classify a page into its different components. Okay, any other questions? Otherwise, I'm going to move on.
Yeah, let's keep going and we can have a Q&A.
Okay, so let me give you, so the first project, at least when it comes to machine learning, is really about data curation from like data selection, segmentation, extraction, as well as data cleaning. The second paper has a very different flavor. It's much more about feature selection as well as building like very sort of flexible models. So specifically, the paper estimates an asset pricing model for the US corporate bond market. US corporate bonds, as an asset class with about $10 trillion outstanding. That's about the size of the US mortgage debt, or about half the size of the US government debt. And in this context, we have essentially a data set where we have a lot of potential features, or in asset pricing, call it conditioning information, essentially candidates that may have some predictive power. That includes 132 macro time series, 41 firm fundamentals, 9 bond characteristics, as well as 10 forward spreads. And so the goal here is essentially to construct portfolios that have the best return to risk characteristics, which is sort of summarized by the Sharpe ratios. So the way how I want to speak about these papers, I want to essentially highlight a few sort of important choices that you have to make along the way when building such a machine learning model in these contexts. Some of them have sort of a more economic motivation rather than a purely statistical motivation. So that's the element that I want to maybe particularly highlight. The first one, obviously, if you build some sort of machine learning model, you have to select an objective function. Usually these are mean squared laws. In our context, we have a sort of an economic framework that gives us essentially two choices. The first is whenever you postulate a stochastic discount factor, you get a moment restriction, which is essentially some sort of expected value that has to equal to 0, which implies no arbitrage. And so we use essentially this moment condition to think about, okay, when would be an asset mispriced? And then we use essentially a loss over all these mispricing errors to find our first objective function candidate. Another approach that is particularly relevant in these contexts is to say, okay, whatever portfolio the machine learning model comes up with, we essentially try to calculate the Sharpe ratio of that portfolio and use directly these Sharpe ratio as our objective function. And so, interestingly, from a theoretical finance perspective, these two approaches should actually yield the same result. There's sort of an intricate link between these two. It turns out, however, that in our context, usually we find that maximizing Sharpe ratios delivers much higher out-of-sample Sharpe ratios. And the out-of-sample Sharpe ratios, that's really what you're essentially interested in, because for that you essentially feed in the predictors, you get an asset allocation, and then you basically get a tradable portfolio that you could theoretically invest in. And so so there's this sort of discrepancy, and which just highlights that once you sort of define the objective function, which is much closer to the economic objective, that means like efficient portfolio construction, actually we get a better performance. It turns out, however, that the mispricing loss actually yields much higher explained variation as well as cross-sectional R squared. So from a purely predictive sense on an individual asset level, you get actually better results using mispricing loss. However, from a sort of a portfolio construction perspective, you get better results using the Sharpe ratio as the objective function. So that's this shows that I think here we can really think a little bit more about the economics of the problem that informs how we postulate our estimation exercise, and it turns out that in a numerical world, this actually makes a difference. Then another thing that is not unique to asset pricing, but certainly very relevant for asset pricing is the regularization parameter choice. Asset pricing, by all means, is an environment with a very low signal to noise ratio. This is unlike like images where, pixels that are adjacent to each other have fulfilled certain properties. For assets, this is usually not the case. And so this makes regularization in the training very important to receive any sort of reasonable performances out of sample. And here, I think the first set of regularization that we do is not like very uncommon. We use like L1 regularization, L2 regularization with different hyperparameters. We use like early stopping, we use dropout. But overall, what makes that a little bit of a challenge is that we come up with like a potential model space of about 768 possible combinations. And so if you have a decent amount of data and limited computing resources, that actually creates a bit of a challenge. I think some of these estimation took more than 3 weeks, and that was a bit of a challenge to secure these computing resources. Now I want to speak a little bit more about regularization that is informed sort of from economic considerations. So in most machine learning applications, we actually pay very little attention to the actual realization of the weights. There's just some sort of background noise. You're really sort of interested more in the ultimate prediction performance. However, here in this context, there's a sort of a nice link between the weights of the model as well as the portfolio allocations. And so specifically the weights of the model imply a certain amount of leverage that a portfolio takes. So leverage in these cases, think about you buying a home and you take a loan and you pay maybe 10% down. So you have a leverage of 10-1. So that can be translated here in these contexts as well, where essentially in a portfolio you would borrow in sort of a risk-free rate or so, and then you would try to invest into risky assets. And so interestingly, if you use like the regularization that I just mentioned before, and you sort of optimize about the hyperparameter space, you would pick out a model that takes on pretty large leverage of up to 20-1. So that's in a finance context, that's a very risky portfolio that you essentially create. The interesting thing is here that we can actually measure the leverage directly by the L norm of the portfolio weights. And so that gives us also a sort of a way to essentially regularize the model already in the training step. There's sort of another interesting consideration here is that the L2 norm yields, because we have like the squared in there, yields typically more balanced portfolios, and more balanced portfolios are considered better from a diversification perspective. So now we had essentially two choices. Do we want to just, directly constrain leverage to a specific upper bound, or do we really want to sort of constrain the L2 norm, which gives us a little bit more intuition about the balance of the portfolios? And however, there's a sort of a nice link between the L2 norm and the L1 norm, as I show here. So W stands for portfolio weights, and N is for the number of assets in the portfolio. So the L2 norm multiplied by the square root of N gives us an upper bound for the L1 norm. And so what we ultimately do is we constrain these right expression by an upper bound in the training stage. And so that's a way that we can in fact discipline the amount of leverage that is being taken on in the training stage, but then also in the validation, in the test set. So just to give you a sense about the performance of our bond portfolios in the test set. So the blue line is the mispricing loss. The orange line is the Sharpe ratio. So first of all, you see there's pretty significant differences in the return profile in these two portfolios that are being constructed. You also see that probably the one where you use the Sharpe ratios has sort of larger drawdowns. So these are periods of negative return. So you see that both in the financial crisis in 2008, 2009, as well as sort of the credit crisis of 2015, 2016. Whereas if you have the mispricing loss, the return profile is a little bit more stable, but the absolute returns are lower. Just to give you a few performance statistics and put that maybe in context. So these are essentially our objective function. That's the type of data that we use for different specifications. So the best model yields a Sharpe ratio of, this is a monthly Sharpe ratio of 0.29, which yields an annual Sharpe ratio of roughly 1.1. That's considered a very good Sharpe ratio, actually. So if you were to invest in the S&P 500, the long-term Sharpe ratio is 0.5. So if you get a Sharpe ratio of 1.1, you probably can raise money to run your own hedge fund. Then in terms of, this is the cumulative annual return. So we get like actually a return of about 16% per annum, which is, I think, really good, given that this is a bond portfolio, not a stock portfolio. And the maximum leverage that our strategy takes on is 4.3, with a mean leverage of 2.6. So that's a reasonable leverage number for a bond portfolio. I'm just going to speak briefly about these slides on finance. We would always think about certain risk factors in the economy, which is associated with an excess return profile. And essentially what this slide shows is that if we use sort of the I would say, generally accepted risk factors in the economy, we still achieve like an excess return after accounting for the risk exposure. So in our preferred specification, we get actually excess returns of 1% per month. So this is about 12% per year, which is, really good. Okay, so with that, I'm just going to leave 5 more questions for questions. The 2 papers are both publicly available if you want to take a look.
That's excellent. Thank you very much, Oliver. I'll stop recording.